and then I.
Yeah, we're good.
Awesome. Okay, firstly, welcome everybody for sparing time today to come and join us in GCC Student Research Day for 2025. And I understand that, it's a bit of a difference of time in different continents, but again, I think it's a massive effort. So welcome all. And my special thanks to all the submissions, all the participants who are presenting today. I have seen their abstracts, pretty terrific work there, and I'm so much excited and looking forward to the presentations today. So without, hang on. So in today's agenda, specifically in this preparatory presentation pack, I'll be walking you through introduction to GCC. I understand that there are almost everybody who knows about GCC, but still it's always good to refresh some memories, and also the presenters who may not have heard about GCC, or is it their first time to come and present at this platform, so it would be good for them to know what GCC is all about. And then we will be spending some time on the GCC Student Research Day, a bit of a history of it, and then I will walk you all through the judging criteria and introduction to judges and moderators, and a bit of program structure. And then we will straight kick off presentations, followed by question and answer sessions and the awards in the end. Okay, so what is Global Communication Collaborative? It essentially is a non-profit organization, and the very intent of the GCC is to bring critical mass to communication research and application through linking leading research groups from around the globe into a coherent collaborative. So now, to make this fancy definition easy for you, what it is all about is that you can only do so much working independently. So the very intent of this consortium was to bring the top-notch universities and researchers from around the world on the same table and build a team that can cater the research and state-of-the-art developments in the space of communication. And at the moment, there are partner universities from around 5 different continents, as you can see up on the screen, and they're all working very closely with each other to deliver value and make communication sustainable for the mining industry. So this is a bit about our board members and also the individual members currently under the GCC umbrella. And of course, they're all very prominent names that don't perhaps need introduction. But I would rather take the opportunity to focus on the fundamental principle on which the vision of GCC lies. I think the principle is that the work that we all do in the form of a team should be enjoyable and should enable researchers to flourish with efforts directed at personal satisfaction and good of colleagues, the industry and society who benefit from the GCC endeavors. So again, it's basically reiteration of the same thing, that working together and delivering the maximum value to the mining industry and at the same time enjoying the work. Okay, so what do we do at the GCC? So really, it's about addressing the challenges of sustainable communication, reducing the waste, improving the efficiency, and reducing the water consumption, and reducing the environmental footprint in any possible way. And as I said, what we do is industry-focused research. It's really applied research and linking the fundamentals to that and to deliver the value. And another intent or objective of the GCC is to collaborate and knowledge share and comprehensive process coverage all the way from comminution going downstream, maximizing the recovery and making our comminution processes more efficient, and catering the sustainability goals. And capacity building is all about upskilling our next generation of metallurgists, mining engineers, or minerals processors. And on the left, you can see there are different avenues that we're catering at the moment, and it includes anything from dynamic simulations, classification, milling, crushing, education, circuit design, and whatnot. And I have added some snippets down there on the right bottom. It was the latest research post Comminution 25 conference in Montagu, South Africa. So it's the only picture that I could find on the social media, but we do arrange lots of this kind of workshops and seminars that gives us opportunity to come along together and collaborate. Okay, so GCC Student Research Day, what it is, when did it start, and why this event? So 3 years ago, I think it got started, and I myself was also a participant in that. I was one of the presenters like you all presenting today. And I think it is an absolutely terrific opportunity to basically showcase your work on the global stage before you go too far in your research journey and you have headwinds. You get early on answers by getting the positive feedback through this kind of environment. And you already see that in today's gathering as well. There are lots of world-level experts who are gathered, and please use this opportunity to gain the feedback. It's a really sort of relaxed environment, and the presentation that you're presenting your work today, it's really should be getting the positive feedback, and that will help you to polish your research further. And we can basically discover the latest developments in the space of communication. And after all, I guess it's a competition, right? So you always compete for the best presentation award. And you guys are the future. And we really intend that, you should be upskilled in a way, and your work should carry an integrity that it takes the flag further, and you shine all the way. So take all from this event today, please. Here is a bit of a judging criteria. I've added this slide. I would encourage all the participants today to take a photo or snippet of it. I think it will help you guide how your presentations will be evaluated today. There are three main components to that. So there is content quality that attributes around 40%. There is innovation and impact that is around 30%, and then the presentation delivery 30% again. And inside each of those components, there are further subcomponents that will be counted towards the final marking of each presentation. So I'll just leave a slide there for a few seconds. And if judges did not receive criteria before, or if they have lost that somewhere in their emails, please take a snippet of it, and it will help you while grading the students. Okay, I'll move on now. So a bit about the program structure today. There will be 2 sessions of the similar style. And first we will have in each session, first we will have 2 presentations, each 15 minutes long. And followed by that would be question and answer sessions, 10 minutes. Right after that, we will have 3 minutes snap presentations, 4 of them. And then following that would be 10 minutes question and answer sessions. Once we have that session completed, and post to that, there will be judges' deliberation, nearly around 10 minutes. And then this will repeat for a second session. And at the end of the event, there will be a prize giving for 10 minutes. A bit of information about our judges. I think it's important for you to know as well that who is evaluating you today, and also about your moderators. So in your judging team, you got Professor Holga, Professor Malcolm Paul, Professor Rodrigo, Dr. Grant Valentine, and Dr. Sherry. And please, again, I would say, try to enjoy your talks. It's a very comfortable, relaxed environment. Don't feel pressurized, and get the most out of it and present the best way you can. And in moderators, it will be myself, and I will be accompanied by Maximilian in the first session, who will be basically moderating that. And after that, again, I will show up for the second session, and I will moderate that. So with that, I will just let Maxim to take control of this. So unless you have any questions, I'll open the floor for the questions. If you got any questions or if you need clarity on anything.
Thank you, Shujat, for this nice introduction into our research day. And I would like to start the first session of today, which is containing some nice presentations about dynamic simulations, stirred media milling, but also bulk solids handling. And I see like Rodrigo is already preparing himself to get up onto the stage. He's giving us an insight into his research about dynamic simulations of crushing circuits. And I think you can start sharing your slides.
Okay.
And also at this point, for anybody who's like participating for the first question and answer session, please write your questions into the chat. So we can, me and Shujat, we can handle the discussion afterwards. Thank you and welcome, Rodrigo.
Just before, sorry, just before, can you hear me?
Yeah.
Yes, Shujat.
Okay, before you begin, I would really encourage everybody, all the presenters, to adhere to the time, please. Just to again make sure that anybody who will go past the allowed time, their marks will be deducted and the time is being monitored. So please respect the time. Thank you.
Okay. So, hello everyone. My name is Rodrigo Prates, and I will present you the work on dynamic simulation of an iron ore crushing circuit. So, for those who don't know me, I'm a material engineer from Federal University of Rio de Janeiro, where I just finished my master's degree on metallurgical and material engineering 2 months ago, and now I'm a PhD student. So I have been working with professors Rodrigo Carvalho and Luiz Marcelo Tavares since 2022 on the fields of process simulation and mathematical modeling of comminution, more specifically using MATLAB and ISO platforms. So the work I'm going to present today is part of a project we have been developing over the last 2 years with Vale. On the dynamic simulation of an iron ore comminution circuit. And the idea is to model effects that cannot be captured using a stationary approach, such as control systems, equipment wear, and operational shutdowns, and then evaluate the effect of these variables on overall circuit performance. So this year we presented parts of this project on different Brazilian conferences, talking, for example, about influence of different mineral lithologies on the crushing stage performance, the comparison between stationary and dynamic simulation to evaluate this operation, and also some crusher parameters optimization. But today, what I'm going to talk about and focus is on the influence of stochastic events, such as truck arrival and operational shutdowns on the circuit capacity. So the goals will be to model and dynamically simulate an iron ore crushing circuit, and then to evaluate the impact of these stochastic events on the capacity of this circuit. Okay, so here we have the flow sheet of the circuit. So first we have the ore being transported by off-road trucks into a primary gyratory crusher. The product of this primary crushing goes to a stockpile that will feed the secondary crushing stage. Then the product of the secondary crushing stage goes to a set of 12 silos that will feed two deck screens, where the material retained on those decks goes to the tertiary and quaternary crushing stages, and the product of both of these stages come back to the screening to be classified again, and then the passing material on those screens are the products of the circuit and go to the grinding stage. So on all of the crushing stages and screening after the stockpile, we have a system of trippers that are responsible for distributing the material alongside the silos, and that is done by a control system that works based on different sensors alongside the circuit. So we have scales on all conveyor belts and feeders, also some level measurements and size distribution sensors as well. So the control system uses all that information for the operational logic, and also to build up some circuit database that we use it for model calibration. So the idea was initially to do the mathematical modeling of the circuit, so the unit operation that will be divided into dynamic and pseudo-dynamic units, then the operational logic being this control system, and then the stochastic events that would be the truck arrival and operational shutdowns. Then we implemented the circuit in the MATLAB Simulink platform. And with that, we can go for the models calibration that use this database. We have over 1 year of information, both from all of the sensors and from stochastic events. And with that, we go for the simulations of the circuit. So we used Monte Carlo simulations, so 150 simulations of 30 days of operation, both for the circuits I just presented and for a modified version of it that I will talk a bit later. So to talk about the mathematical modeling of the units, for the units that have a material resistance time of minutes going up to hours, like silos, conveyor belts, and stockpiles, we use it in dynamic models. So we have material accumulation. And here I would like to highlight the modeling of the stockpiles and silos. They are basically a first in, first out model, where the units represented by a sequence of perfect mixers. And for each mixer, we are solving the differential equations for mass balance and size distribution balancing and other properties. And for the conveyor belts, we are using a fixed time delay. And for units that have much lower residence time, like crushers and screens, we are using pseudodynamic models. So for the crushers, we are using the Whiting model, and for the screens, a modified Carha model. And for the stochastic events, in the case of the truck's arrival, we are modeling the time between trucks and the ore mass per truck. And for the operational shutdowns, we are talking about preventive maintenance, so scheduled maintenance and also corrective maintenance that comes from failures. And in this case, we are modeling the time between the failures and the time to repair. And to model all of these, we used the Minitab software to determine what was the best distribution in each case, so log normal distribution, variable distribution, and so on. Well, so going for the results, first, here we have the modeling of the truck arrival. So in blue, we have the measured data, and in red, the fitted distribution. So in this case, for example, for the time between trucks, we use the log normal distribution, and for the ore mass per truck, a normal distribution. And what I would like to highlight here is that if we do not model any of the operational shutdowns, the mean capacity of the circuit is around 2,900 tons per hour. And this is a number I will come back later. So going now for the maintenance shutdown. So first, the first thing we did was to group equipments that caused the same stage to be shut down. So for example, circled in purple, we have 3 conveyor belts, and if any of these conveyor belts that are responsible for transporting the material that comes from the screens, if any of these conveyor belts are shut down due to some failure, we need to shut down the whole screening stage. And the same thing happens for the primary crusher and this conveyor belt that transports the primary crusher product to the stockpile. So we grouped these equipments, and for each of these groups, we have scheduled maintenance of 12 hours, and also we modeled the failures and corrective maintenance. So we have the time between failures and time to repair for both of them. And lastly, we also modeled the breakage of the other crushers, so secondary, tertiary, and quaternary crusher. But in this case, if one of these crushers fail, we don't need to stop the whole, for example, the whole tertiary crushing stage. We just need to stop one of the production lines, and it can be repaired. And to evaluate the effects of this modeling, we can look for the stockpile dynamics. So here, at first, we have the feed rate for the stockpile during 3 days. This is a function of the truck arrival. That's why you see such a big variability. So sometimes there are 15 trucks in an hour, sometimes just 5. So that's why you have all of this variability. And during some times, for example, after 48 hours of simulation, up to 60 hours, we don't have any material coming into the stockpile. That happens because we have some operational shutdown happening on the primary crushing stage. So that's why we have this stoppage. And for the discharge of the stockpile, on the other hand, it is made by a set of 6 feeders that are under the stockpile, and the number of feeders that are operating parallel during different times depends on the stockpile level that is controlled by some operational logic. So that's why you see sometimes a discharge of around 3,000 tons per hour, and sometimes it decreases. And close to the 60-hour mark, it even got to 0, probably because the stockpile level got too low. And we can see here the actual effect of this dynamic. So we can see the changes in the stockpile level. So circled in purple, we have the effect of the scheduled maintenances. So in this case, we have a 12-hour maintenance. So due to this longer time of stoppage, the stockpile ends up reaching its minimum or maximum level. And at this case, we need to shut down the whole crushing circuit, compromising the maximum capacity. On the other hand, when we only have, let's say, some corrective maintenances happening that can take around 3 hours to 4 hours, that is not enough for the stockpile to reach its maximum level. So the stockpile is able to absorb the impact of those failures, and we don't lose capacity. And circled in green, we just have the usual operation where the control system tries to keep the stockpile around 40 to 50% of its level. So that was an example for one simulation, and what we did was 150 simulations of the circuit, and with that we could create this distribution of the cumulative probability for the monthly production. And as you can see, we have 16% reduction on the main circuit capacity when you compare this modeling to just the truck arrival modeling. But something we noticed is that the failure of individual crushers had no effect on circuit capacity, and that happens because this circuit is overdimensioned. So, for example, we only need 2 tertiary crushers to be able to process the amount of material that comes into this stage, but we have 4. So what we did was create this modified circuit where we reduced the amount of equipment. So let's focus on the tertiary for now. That goes from 4 to 2 crushers. And what happens in this case is that a lot of times we actually reach the maximum stockpile level because we need to stop the stockpile discharge, because since these crushers failed, we don't have enough equipment to process the amount of material that is coming from the stockpile. So we need to reduce the capacity or stop the circuit during some time. And with that, you can see that our monthly production decreases even more. So for the original circuit without shutdowns, we have around 2,900 tons per hour, and we got up to 600 tons per hour less with this modified circuit with the shutdowns. So some conclusion of this work. First, it was possible to dynamically simulate this industrial iron ore crushing plant. The modeling of maintenance shutdowns led to a 16 decrease in circuit capacity, showcasing the importance of taking that into consideration. And these simulations with a modified circuit showcased the importance of equipment redundancy to absorb these eventual failures. So you don't need to use all the 4 crushers, but if you don't have them, maybe sometimes you end up losing capacity. And for the future steps of this work, with the further development of the control system and addition of stuff like equipment wear, we plan to daily use the simulator as a digital twin of the circuits, both for just supporting decision making and in the end, maybe the participation in the circuit's automation. So here are my announcements, and thank you for the attention.
Thank you, Rodrigo, for this nice talk, especially regarding the time in Brazil, 6 a.m. So
yeah.
yeah, very interesting talk, and also congratulations on like finishing your masters and now working as a
Thank you.
PhD. And yeah, I would like to encourage people to send their questions into the chat. And also perfect timing, Rodrigo. And yeah, next on the stage, I would like to welcome Kabeli from UCT. And yeah, the question session will be after the talk of Kabeli. Yeah. Okay, we can already. Hey, okay, we can see your screen and we can also perfectly hear you. So,
all right. I'll be presenting my research on investigating the impact of state milling to improve the product finance for PGM tailings reprocessing. For this part, it's the HIG mill case study, and this work was done by myself, Megan Becker, Kirsten Corin, and Aubrey Meinzer. It forms part of our growing effort to optimize tailings reprocessing for better PGM recovery and sustainable mineral processing. Tailings reprocessing has become an increasingly important strategy to maximize PGM recovery. However, key challenges lies in the fact that most of the PGMs found in the tailings remain or are not liberated fully. Traditional strategies or traditional grinding, traditional methods utilized such as ball milling are known to be lead to high energy consumption and also leads to excessive slime generation, which leads to high metal losses. Fed millings, however, have been proposed to deal with efficient fine grinding with proven success in producing a controlled and a narrow particle size distribution. The HIG mill, which is owned by Mezzo, it utilizes inert ceramic media and it operates in staged grinds between each grinding rotor or the static counter discs in the grounding chamber. It also does not require any external classification device as the coarse particles and media are centrifuged within the grinding chamber, and the overflow. It is fitted with an overflow fitting for the ground product particles. The application of stirred milling in the PGM industry, or rather in the mineral processing industry, has seen a significant growth inspired by Anglo Platinum, which is now Valterra. They, however, utilize a HIG mill, no, an ISA mill, which has been or shown to been proven to enable tailings retreatment on oxidized and slow floating PGMs. And its application in the PGM industry includes in mainstream inert grinding, where they optimize recovery, and in ultrafine grinding, where it is utilized to optimize grade. In this study, we will be utilizing, or rather this slide shows the proposed or the utilized process flow sheet, focusing first on the top route, which is the stirred milling route. We use the HIG mill, which utilized 3.5 millimeter Keramax media. In it, the prepared slurry or the prepared sample was ground and evaluated for flotation response using batch flotation. We also utilized a different route where we used a ball mill, which in this case, it was not to necessarily to compare the performance between the ball mill and the HIG mill, but rather for minimal regrinding that can be achieved in a HIG mill, in a ball mill, which is, as it would have been, it would not make sense to use a HIG mill or a stirred mill to repolish particle surfaces. So what was done with the ball mill was just to merely repolish particle surfaces and make them amenable for flotation response. And we also investigated a case where there is no regrinding done. In this case, the feed as received from the mines was reground straight as it is. Our feed, which is the tailings from Impala Platinum mine operations, were given by Tailings Technology, which runs their tailings reprocessing plant there. It is a very low grade tailings reprocessing, as it is a very low grade ore, as this is the ore that has undergone significant recovery stages, including a tailings scavenging plant. In this experiment, or in the grinding experiments, we achieved the pH targets of 83 microns in a ball mill and 74, 50, and 28 in the HIG mill. For flotation response, as our primary focus was recovery, not grade, we only used a collector and a frother. With it, we used the SIBX as a collector and Senfroth 516 as a frother. We were not really concerned about the chromite entrainment or its effects in our concentrate, as most of the chromite was also recovered in the preceding recovery stages, as the Impala also fitted has a corresponding or an adjacent chromite recovery plant next to it. The analytical tools utilized, we did some mineralogical characterization of the feed using ChemScan backed by XRF and XRD, and we also did particle size distribution analysis of all the ground products in the feed, along with fire assay, which was coupled with ICP-OS on the concentrate, on the flotation concentrates and tailings. To talk first about the feed mineralogy, or rather the feed characterization. This graph shows a pie chart which was created using the bulk mineralogy characterization that we performed on our feed. In it, we have a significantly high proportion of pyroxenes and other silicates, accounting for over 60% of what's in the sample. We have almost 29% of chromite, which is slightly lower than the typical UG2 tailings, owing to the fact that there are chromite recovery plants fitted along the value chain of the ore that we received. There are minor base metal sulfides. There's a minor constituent of base metal sulfides that were found in the biomineralogy, and these are of importance in our research as they provide a reason, or they could be of economical importance in our research. However, there was a concerning amount of phyllosilicates at 6.9%, as these are components that could lead to high amount of silicates, no, not silicates, high amount of slimes, and also there was a talc within this phyllosilicates which could contaminate our concentrate, as talc is naturally floatable. We performed some preliminary PGM liberation and association analysis, and in it we were able to establish that there's a significant amount of PGMs that remain entrapped and encapsulated within the gangue minerals on the feed, which explains why, or rather why they were found in the tailings in the first place. There's also a significant amount of base metals, which are also valuable, and we'll be looking to recover those. And through this, they further confirm the value or the potential benefit of grinding further to improve liberation prior to flotation. This slide shows the particle size distributions achieved for the pig mill tests performed at different rotor speeds, along with the graph on the right, which shows the relationship between the specific energy consumption with the rotor speed at different grinding times. In the particle size distribution graph, we can see that with increasing the rotor speed, the particle size, we achieved a narrower particle size distribution with the increase in rotor speed, with a preferential grind on the coarse particles, leading to a narrower particle size distribution and a more desired particle size range, which is beneficial for our flotation response analysis. We also observed that there is the specific energy analysis followed an exponential trend, meaning that higher speeds yield finer particles, but at the cost of a higher energy input. This graph here shows, the first one is the relationship between the specific energy and signature plot, and which is basically the specific energy versus particle size, which is basically the signature plots. In it, we do see that there is an exponential increase in energy. There's an exponential increase in energy demand as the particle size grows finer. However, one interesting observation is that the rate of increase of energy decreases with the increase in rotor speed. This is attributed to the fact that as you grind faster, there is high energy imparted onto the grinding media, leading to more effective comminution or more effective particle breakage. I also plotted here the relationship between the stress energy, the specific energy, and the reduction ratio achieved. We can definitely do see that as the specific energy increases, there is a corresponding increase in stress energy along with a corresponding increase in the reduction ratio. Although in some cases there's a dip similar to the one observed at this point at 19.62, this is primarily because there is an increase in energy due to the increase in grinding time rather than the increase in tip speed, which is what generally increases the stress energy. We also plotted the relationship between the specific energy with the rotor speed for different grinding targets, which were utilized for the flotation response. And in this graph, we see that this graph was derived from the signature plots that were determined or shown earlier. And in it, we see that there exists an optimal rotor speed corresponding to the desired target size, grind size. As you can see that the specific energy consumption increases with increasing rotor speed, but the curve increases in a there's a decreasing trend. So the gradient decreases as the rotor speed increases. However, as much as this data could show that operating at high speeds in stirred media or stirred milling would be beneficial, there's also a potential impact of grinding media wear and the equipment wear, which were outside the scope of this research. Hence, in most cases, we do know that although it's possible to go very high in stirred milling, to go high in rotor speed, on the rotor speeds of the stirred milling devices, sometimes it's not necessary to go that high, as it could lead to other costs, including the wear rate and the machine wear. In this graph, we plotted the relationship between the 4E recovery of our valuable minerals versus the mass pool. What is evident in this graph is that the 4E recovery increases significantly with grinding finer, and this is shown by the fact that the slope of the recovery solids or the recovery mass pool increases as the particle goes finer. We also plotted the relationship between 4E recovery with the product size or the PAT of the ground product, which is the feed to the flotation sample. And there's this distinct difference between the 4E recovery achieved in stirred milling and the one achieved with ball milling in the base condition. And although at this point we do not have a specific answer for why there is such a stark difference between the recovery in the ball mill, as much as the particle was significantly coarser than the stirred mill product, it is not along the same trend line that we observe on stirred milling, which could mean that there are other issues that could have led to the ball milling performance being this low. Some of those could include the generation of slimes that we have already attributed to in ball milling. Then in this graph, we show the relationship between the upgrade ratio. Yes?
One comment. Watch the time, please, and maybe, try to find an end.
Okay, I'm almost there. This is the second last one. In this graph, we show the relationship between the upgrade ratio and the recovery for e-recovery. In it, we can see that the upgrade ratio achieved in stirred milling is significantly higher than the upgrade ratios achieved in ball milling in the baseline condition. And with that, the authors did conclude that although there could be improvements in ball milling, they are limited by the residence times usually required in ball milling, and there is minimal recovery improvement. That milling showed high improvements and very efficient in energy. We do recommend to utilize or rather perform more studies in other stirred mills. As in this study, we also use the heat mill, another mill, which similar response. And thank you for everyone.
Okay, thank you. So timer was still okay. And yeah, thank you for the interesting insight into your research. And yeah, I will wait a couple of seconds for people like to put in their questions into the chat. Okay, there's already the first question by Marcelo, he's asking you, Kabeli, did inert grinding media also used in ball milling or steel media?
Now, in ball milling, we used steel media because that's a more comparative response in that ball millings are usually operated using steel rather than ceramic.
Marcelo, you want to comment on that?
Yes, just to complement. So in the flotation side, do you think the steel would have actually the iron from steel wear potentially have any effect, or it's really too little to consider? Because there's a lot talk about the benefit of inert media in ultrafine grinding in PGMs. I was just wondering if you would attribute any effect to that, or it's too little.
Yes, there is some effect that we could attribute to the fact that, to the difference between stirred media, not stirred media, ceramic media and steel media. But we felt that at this point of our research, it would be going a bit too far to actually investigate how the impact would change if we utilize a ball mill in the ceramic media in the ball mill. Yeah.
Thanks.
And another question from Grant to you, Kabili. He is asking if you measured the EH, pH, and DO. Like, I don't know the abbreviations for EH and DO, but
okay, that's no. I didn't measure any of those because our flotation response was primarily as a diagnostic tool of combination experiments. Therefore, we didn't do much investigation in trying to keep things within a certain pH or what. We just used the same recipe for everything out.
Okay, thank you. And another question to you from Holger Liebowitz. Maybe you can share your slides again, because he has a question regarding slide 8 and the particle size distributions.
Yes.
He's asking, like, on slide 8, the particle size distribution of after 289 seconds, grinding was coarser than after 149 seconds. Specific.
Oh, somewhere here. There's no time.
That's rotor speed, but on
Yes.
the right hand
so this
side,
side
it's specific energy and.
On the right-hand side, it's specific energy and rotor speed at different grinding times. Nothing about the particle.
Okay, Professor Lieber, do you want to comment on that?
Yeah, I just have to look. I was curious at. I think I'm referring to the left side. I was referring to the 550 RPM, that's finer, and the 450 and the 350. There's no major difference. That was the one I was missing. Yes.
Oh yes, we did observe that, and for now we couldn't come up with the actual reason as to why the two seem to be in close contact. Yet, when we went higher, there's a significant change in the particle size.
Okay.
We hope that it's maybe attributed to our machine inefficiencies or our screening or analytic analysis.
Okay. Yeah, thank you.
Okay. Thanks.
Sorry, Max, before you go to the other comments in the chat, Cynthia had her hands up, I think. So she had a question. If you want to take her question first, please.
Okay. Sorry. Didn't see that. Cynthia still here? Okay, maybe later. So maybe we move on to Rodrigo. Grant has a question. He's asking, given the small reduction in throughput with half the installed crushers, would you recommend installing standby crushers in the application?
So, I mean, the circuit, this specific circuit is way over-dimensioned because we had some conversation with people from the operation about this, but they were planning like they thought this, let's say some crusher would have a capacity of 400 tons per hour, and it ended up being the double. So it's way over-dimensioned, but even so, I think like you at least one crusher as a standby is always beneficial, especially thinking about the future, like more competent mineral coming into the circuit. So yeah, even though right now the decreasing capacity is not that high, to have it for the future, yeah, I think it's very beneficial.
Okay. Professor Lieberwood, do you want to comment on that? You're raising your hand.
Yes, I have a question. Rodrigo, that's an interesting topic. Did you ever look at the feed particle size distribution, which is acceptable to these crushers in comparison to the secondary crushers? Because typically, if you have underutilized comminution steps, it might be interesting to shift more work to these comminution steps by essentially opening up the secondary crushers also. And so you might increase the capacity of the whole line this way.
Yeah, so we didn't look specifically on the secondary crusher, but we had some analysis on the trying to optimize the circuit by changing the size, closed size aperture of the tertiary and quaternary crushers. But yeah, like the circulating load of the circuit is very low. So one of the discussions were even like we thought a good amount of the material could just bypass the crushing stage. So we have discussions on that direction, but yeah, I think overall all the crushing stages of the circuits are kind of over-dimensioned and being underused, I would say. But yeah, that's definitely a discussion.
Okay, thank you.
Thanks. There are like 2 more questions, but maybe you can yes answer this one like afterwards in the chat. I would like to move on to the snapshot presentations. Here we have Luciano from UCT who's going to start first. To all 4 speakers, would be nice to watch your time limit of 3 minutes. It's not too much, and we are looking forward to questions. And Luciano, if you're here, please share your screen.
Can you hear me?
Yes, perfect.
Can you see my screen?
As well, yeah.
Okay.
Good.
Thank you. I'll be taking you through a screenshot of my work that I'm currently doing, which is the reprocessing of the slag and tailings for the resource recovery. The aim of this work is to improve the recovery of the PGMs from slag and tailings by fine grinding using the SMD mill. And to do this, we'll be investigating or optimizing the operating parameters of the SMD mill, which is the stirrer speed, the media size, and the mill fill, based on the energy consumption and the product size. And for improved recovery, we'll be measuring it using the flotation and the leaching. And we'll also look at how this processing can influence the flow sheet design. And so we are using the stirred mills because we know that they achieve fine materials at the lower specific energy, and also because they produce a controlled particle size distribution, which is able to be managed by the flotation side of things, where they can be able to manage lower PATs as opposed to a wide range of particle size distribution. And so my experiments includes 27 experiments of grinding both the slag and the tailings, and then the ground material being floated, and then the concentrate will be leached to assess the recovery. And so these are the kind of results that I'm having, or the results that I have from grinding the tailings. It's just the preliminary results where it shows that I have a reduction ratio of about 9 for using 3.5 millimeter ceramic media. And it shows that the media of size 3.5 and 2.8 millimeter show similar product sizes. On the energy, on the specific energy, it shows that the increase in media size increases the specific energy. And on the PAT side, it shows that the smaller media sizes, or it's opposite with the PAT, where the higher size of the media, which is the 3.5, produces smaller PAT sizes. And that's it for the screenshot of my investigation. Thank you.
Thanks. And yeah, I will head over to Philip from Freiberg, who's going.
Oh, how do I stop this? Oh, stop sharing. Okay.
Stop. Okay.
Okay. No, thanks.
Thank you, Lovian. And yeah, I will head over to Philip, who's also going to give us some insights into dynamic simulations. Yeah, please, Philip.
Yes. Thank you, Max. Can you see the screen and hear me?
Yes. Everything is
Great.
perfect.
Great. Yes, I'm Philip Niebel. I'm going to introduce you to my current work on dynamic jaw crusher simulation. This is part of my new project I'm working on at the beginning of this year. It's a dynamic flowsheet simulation DICEL project, and the objective is to develop advanced models for especially crushing and screening for ore and rock processing, and also, for example, for accurate production. So I focused at first on jaw crushers, and I combined the population balance DICEL approach and the multi-stage crushing simulation approach, what you can see in the picture on the right. So the crushing chamber of the jaw crusher is divided into several number of crushing stages. I do this with the help of a transport model. So based on the crushing kinematics and the geometry of the crusher, the number and the geometry or the parameters of the crushing stages are calculated. And each of these stages consists of a selection, a breakage, and a classification function. And on top of that, I also added a time delay unit in the DICEL model so that I can calculate not only the particle size distribution, but also the residence time, which I think is a little bit more interesting and new. And that is why I brought a first example thereof, which you can see here on the slide. In the example, I fed petalite particles into a double toggle jaw crusher singly, and I measured the residence time manually by hearing in the jaw crusher. This is a problem, so the plot has I would say a limited meaningfulness because the measurement of the residence time is not really accurate. But as you can see, the tendency of the influence of particle size and the residence time of particles in the crusher is predicted well. By the way, of course, the particle size distribution is also predicted well. As a next step, or what I already started, is I implemented the power and the force calculation into the crusher. And due to the multi-stage approach, it's even possible to plot the force distribution across the vertical dimension in the quasar, as you can see in the picture. And also, as the next steps, I want to test the model for gyratory or adapt the model for gyratory and cone quasars. And I want to develop advanced models for screening machines as well as for impact quasars to depict complete flow sheets dynamically. So that's all. Thank you from my side.
Okay, thank you, Philip. Next on the stage is Mateusz from Rio, and he's going to talk about bulk solids, I guess.
Hello, everyone.
Hey, we can hear you, but I cannot see your screen yet.
Are you hearing me?
Yes, we hear you.
Okay, I will share my screen. So, hello everyone. My name is Matheus Braga. I'm a master's student. I'm under the supervision of Rodrigo Carvalho, and my work is on measurement of iron ore saturation moisture content.
I will shortly interrupt you. Can you maybe put on the presentation mode? Right now we can see your slides, but only like the view.
Sorry. Can you see now?
Yes.
Oh, sorry. Okay, sorry. Okay, start again. Hello, everyone. My name is Matheus. Today we will present the work on measurement of iron water saturation moisture content. I'm under the supervision of Professor Rodrigo Carvalho. To begin, iron water handling presents some challenges. The material contains a broad particle size distribution. The material also is exposed to natural moisture content and sometimes exposed to rain. These characters can lead to handling issues. Common operational issues in handling operation are transfer chute blockages, conveyor belt misalignment, and material handling is influenced by forming factors, which are moisture content, particle size, apparent density, and chemical composition. The objective of my work is establish a methodology to determine the saturation moisture content of different iron ore samples and correlate the chemical composition of the samples and particle size with the handling behavior. I worked with two different Brazilian ores that have different particle size and chemical compositions. To investigate that, I developed the vibratory table system. You can see in the top right on the slide. And this vibratory table system was able to give me the saturation moisture content for the samples. And these values of moisture saturation moisture content will support my label skyro handling tasks as drawn down, rotating drawn, and angle of repose. Now I'll show you some preliminary results. And the experiment was able to capture the saturated state. Here you can see the expansion rate on the video. As we go adding water, we can see that the iron ore piles, they reach a critical state that are known to cause handling problems. And here I have the results for saturated samples. We can see the water reflection on the movie, and we can establish that the iron ore pile are saturated. For further work, the next step is model the expansion rate, determine the saturation moisture content and the critical moisture content for different iron ore samples. And for selected moisture levels, laboratory scale tests will be conducted for DAM model calibration. The acknowledgements. Thank you, everybody.
Thank you, Mateusz.
Thank you.
And last but not least, it's Julio.
Right. Can you see my screen, Max?
Yes.
Yep.
And we can also
Is
hear
it in
you.
the presentation mode or?
Everything is good, yeah.
Okay. All right. So, hi, everybody. I'm Tulio Campos, a PhD student at the Federal University of Rio de Janeiro in Brazil. And today I will present the work Real-Time Simulation of Stockpile Level Dynamics in Comminution Circuits. So stockpiles are usually the connection point between crushing and grinding stages in comminution circuits, as presented here in this diagram. And it's quite important for us to map how their behavior can impact both upstream and downstream operations, especially here in this work when looking into variations in the stockpile level dynamics. So in order to cover this topic, this present work here proposes a discrete event model that will be able to capture real-time variations in a surge stockpile mass level based on production flow rates from the crushing and grinding comminution stages. To do that, we selected here the Minas Rio comminution operation from Anglo American here in Brazil. It will be our case study. And there is a top view of the plant here with the stockpile, the crushing stages, and the grinding stages. So data was collected from the process and relied on solid flow rates and operational shutdowns from crushing and grinding circuits. And being these operational shutdowns divided in three main groups: unplanned, planned, and stockpile level shutdowns. To describe this stockpile level dynamics mathematically, we are proposing this hybrid modeling approach divided in three main modes as presented here. The first one relies on the Monte Carlo algorithm in order to predict the solid flow rates and was calibrated based on historical data from the process for both crushing and grinding stages. After predicting these solid flow rates, we can incorporate now the unplanned and planned operational shutdowns here in both stages. And by the end, the last piece of this puzzle relies on a deterministic part of the model with a mass balance and a stockpile level control in order to predict the mass of material on it. And the operational shutdowns associated with stockpile level will be an output of this model. So in order to apply the model here and demonstrate how it is used, two case studies were simulated. The base case relied on almost equal average feed and reclaimed solid flow rates as presented here. And the scenario one was basically one idea here to increment in 1% and 4% in respect to the base case, the average solid flow rates that will be feeding and being reclaimed from the stockpile. So with this model, we can see the profile over a 12-month period, highlighting here the differences between both base case and scenario one. And the model could also predict here the operational shutdowns that were caused by problems with stockpile levels. It was interesting to note that although a 4% increment was designed in the grinding circuit in scenario one, only 1.1% was really reached given the limitations achieved with low stockpile levels. Well, basically the modeling approach demonstrated ability to capture real-time variations in the source stockpile level dynamics. Different operational scenarios revealed distinct stockpile behaviors, and the hybrid modeling approach shown potential to be applied as a tool for investigating different operational scenarios and the strategies. So thank you.
Okay, thank you, Tulio. Thank you to all for speakers of the snapshot presentations for watching the time. And there's already one question of Professor Lieberwood to Mateusz, and he's asking if the chemical composition is relevant or maybe the mineral composition. Maybe you already had a look at it because
Hello?
there was, hey, yeah, we can hear you.
Can you ask again, please?
Okay, the question is if for your test, is the chemical composition relevant, or maybe more the mineral composition of your material?
I believe both, because the sample B has more alumine content. It's nearly 20%. But I haven't found any correlation yet. I worked only with 2 samples, but I have more samples to work. I have 5 actually samples to work.
Okay,
But
so
they are correlated.
Okay.
Chemical
So,
composition and
okay, thank you. So there's more research to be done
Yeah.
and to see like which characteristics influence these results. Then there was one comment to Ljubljana from Grant. He's recommending looking at the PE98 and P80 ratio. It appears that the coarse particles are not being broken. Probably this is like a comment on for lower tip speeds. And I don't know, did you already check on these values?
I think for the lower tip speed, I think we are constrained by the SMD that we're using because it's the batch one. But instead, we also increased the sizes of the media. We now incorporating the 5mm media into that to look at also the feed top size and see if it can be crowned.
Okay. Maybe one further question to you right now from myself. Are you looking to improve like the particle size distributions, or also like the throughput? What is your main goal?
Well, throughput is currently on hold because I'm currently investigating using the batch SMD. So the throughput is kind of on hold, but I'm also looking at it, but after optimizing the operation.
Okay. Okay, then going on to Philip, one question from Grant again. He's asking, what is the relative importance in the dynamic modeling of crushers screens where this material is handling in crushing circuits? Grant, I'm not sure if you're here. Philip, can you comment on that?
Yes, sure. Thank you for the question. Well, I think the dynamic simulation of the crushers, what I presented shortly and really in this detailed level, is maybe more important for crusher dimensioning, for example. So it is less important for things like plant capacity. So materials handling is more important, I think, for plant capacity. But what I showed, for example, the forces in the crusher can be important for wear prediction, and this will influence maybe the interval of maintenance.
Okay.
Yeah, no, good. Thanks for that.
Okay, perfect. So I think, or Grant, do you want to comment further?
No, I thought it was a good presentation. So I was just wanting to know whether there was. I'd never thought of the dynamics around crushers being as important in a crushing circuit. So I'd always thought it was about the materials handling and the bins filling up and emptying. But it's a good answer.
Okay, perfect. Maybe during the break, someone has also figured out what to ask Tulio. Maybe he's eager to answer within the chat. But I would suggest like during the break now for maybe 10 minutes. So we will meet like 26 past 11, so or 26 past the full hour wherever you are. And maybe we can have a cup of tea, coffee, or anything to drink, and we will meet in 10 minutes, starting with the second session. And thank you for all speakers, and see you in a couple of minutes.
See you.
All right. Can you hear me?
Yes.
Awesome. All right. So I'll take over. Hope you all had like a cup of tea or coffee, whatever you wanted. So we will resume from here for our session 2. Firstly, great talks in the first session. I must say it's not easy to keep up with the time, but great job done, all of you guys. So without any further delay, we will move on to the second session with the first talk presenting Seema Helmers, and the topic is comminution and liberation modeling of metallurgical slags from mineralogy to predictive grinding behavior. So Seema, please, over to you.
Thank you. I hope you can hear me and see my screen.
Yes, all loud and clear.
Okay, thank you so much. So I will start here. So welcome to my presentation. Today I'm going to talk about the comminution and liberation of the slags. First of all, sorry, I have to see the next slide. Okay, it should work. Okay, about me, I studied material science and engineering and mechanical engineering, and I'm from TU Braunschweig, Germany. I started with my PhD in 2022, and my topic is comminution of slags. So we already heard a bit of slags, but let's see what it is exactly. Basically, it's a byproduct of a primary or secondary production of metals, that is from the ores or recycling. And most of the time it's used in construction materials, but recently it has been a focus to be used as a secondary source to recover our valuable material. So to achieve this, there was the idea of engineered artificial minerals. That is, we have this slag that is really hot, around 1000, 2000 degrees. So we use thermodynamic modeling and we control our cooling so we can have our target elements in certain phases. And then using optimized comminution methods and liberation methods, and we can get to our target particles. So it looks a bit like the ore industry, what they're doing, but it's not that easy. And then I will tell you why. If I look at the nature of ores and compare it with the slags, we can see that in the ores we have a long time for the phases to form, so everything is predictable. They have a very nice crystalline forms, and over the time we have well-established processes for different elements. On the other hand, the slags, even the engineered ones, of course we can control the cooling, but the grain boundaries are still sharp. We have dendrites around the cubicles. We have a lot of amorphous phases, and there are a lot of mixed crystals, so it's not that easy. So the question is that can we use the process that we already have on the slags? And even if we can do that, how we can tailor it so we can optimize the whole process. That's the focus of my study. So how to get there? The first step is that to develop a framework that connects comminution and liberation. Based on this data and having the framework, then I can design my comminution processes from crushing to fine grinding. And then, based on what there comes, I can understand, okay, how can I optimize the whole process and improve my results from the point of view of the energy and, of course, from the recovery. So let's move to the first one. The first step was comminution liberation framework. For this one, I used different slags, and then most of them were synthetic. That is, different oxides were used to produce a similar slag to lithium-ion battery recycling slag. The main phases that there were lithium aluminate oxide, lithium aluminate, and eucryptite as the phases that they contain lithium, and then gehlenite as the gangue material. I used several different crushing steps, and until I got to 500 micron. And then I used different feeds using a double roll mill to have a very narrow distribution of the particles, so I could study the effect of particle size in flotation. How did it work? There were 3 different parameters that one of them was the speed of the roller. So here idea was that to use different gap sizes and different rotational speeds, and of course changing the mass flow. What could be measured is that to use a specific energy to see that which of these variables are efficient and which are not. So let's look at the different processes. What we can see that basically, if it's define the energy utilization, that is the energy that we need to produce new surfaces. The more it is, the more efficient is our process. So there are 2 aspects that play a very important role in it. One of them is the feed size that we have, and the other one is the gap size that is relative to the feed size, changing from 30 to 60%. The mass flow and the variation of the circumferential speed did not play a very strong role in our energy efficiency. So what happened there? We produced different sizes and then fed it to the flotation cell to see that which one was more efficient. To look at this, the first step was the flotation, and then based on what was in the flotated part, that was the target, our first target was lithium aluminate. So this one was done and then added to the leaching. The best size that we had was around what was under 100 micrometer, and they had a very high yield. That means that a lot of material were flotated. But when we introduce it to the leaching, we realized that we don't want to have a lot of argon material in our feed. So the best recovery rate were over 30 micrometer. Based on this study, we could find the best target size that was between 30 to 100 micrometer, and then we had the best combination for our milling that was energy efficient. The flotation target phases that we used were lithium aluminide or eucalyptite can be used as well. The focus, we had a framework and a window to work at it. It was whatever under 100 micrometer, and we had the parameters for our roller mill. So let's look at the next part. We have a target size and we want to reach it using different mills. We can start it like usual ores, that is, we can start with a jaw crusher and keep on reducing the size using secondary crushers like impact mills and roller crushers, and then using the finer particles that are below 500 micrometer to another roller mill and grind it so we can reach our particle size. Of course, most of these processes were just done once as a single pass and not in a circular way. So at the end, it could be that suggested that there is a circuit for the fine grinding, because we need to grind and grind and grind to achieve our target size. Of course, we can put different classification methods and increase our recovery. My focus here would be on the secondary crushing and grinding. So what we had 2 crushers. One of them was an impact crusher and the other one was a roller crusher. And 3 different feed sizes were studied from 1 millimeter to 1 centimeter. And then the size-specific energy was calculated to see how efficient our process was. And the focus was to achieve the 100 micrometer. So why didn't we use the surface? Because the particles were pretty big, so it was difficult to measure the surface. So in this case, we use the size-specific energy, and the higher the size-specific energy is, it means that we are putting too much energy to produce the same finds. So as we can see, impact is not that efficient, but when we look at the compression, we see that for the higher and bigger feed, we have the same behavior. Only when we look at the 1.7 millimeter feed, we can see that we have a better energy efficiency. Another thing that we saw was that an impact mill for the larger particles, around 1 centimeter, the particle size was a bit strange. There were really big particles, and then there were very fine particles around 1 millimeter. If we look at the slag, we can see that there were metal droplets, and with the first impact, we could get these metal droplets out of the system, and then after sieving, we had the slag on its own. So we can say that we can use impact milling to liberate these metallic droplets and facilitate our pre-separation. And then we use a roller mill to reduce the gap size step by step and reach our target size. So let's look at the comminution process if we had a circuit for the fine grinding. There were two options that we have. One of them was the circuit operation, that is, we had a feed size, we had a specific gap size with a certain circumferential speed, and we did the grinding. Then we had our target size of 100 micrometer. We sieved this part, separated, and we added exactly the same amount of the product to the new feed, as a new feed, and then with the coarse particle, we did the grinding again. This was done again and again and again, and until a stationary state was reached. And the other approach was a series of operations. That is, we had a feed part, and we set the gap size. We grind the material, but we did not sieve. We just analyzed the particle size distribution and adjusted the gap size and speed based on this new product, and then adjusted several times until the whole material that was in the system reached the desired particle size. So let's look at the energy values. The first one was the series. That is, we had multiple passes and we didn't do any classification. As we can see, by increasing the stressing event from the first to second to the third, the energy increases because the defects in the material are reducing. And the other hand is that by increasing the gap size, we have to increase our stress events because most of the particles fall within the gaps. And another thing that is important is that we have to look at the cumulative specific energy, because we need the whole energy for all the stress events to reach our target. On the other hand, for the circuit operation, we have multiple passes. That is, we do it for the first, second, third, and fourth time until we reach a steady state. But the gap size and the speed remains constant. So how do we evaluate our process? We use the size-specific energy, like for the crushing. Here we have a sum of specific energies for the series, but for the circuit, we saw that we have reached in a level that after repeating the third or fourth time, we do not need to need to repeat it. The amount of the product would remain. So we take this as our yield, and we just take this energy and then calculate our size-specific energy. and we can look at the energy utilization, and we can see that basically by increasing the gap size, the energy utilization increase, but then we have less product. So we can use the for the larger fits, we can use the circuit part, and then for the smaller fits, we need this constant. We can keep on sieving and then reaching our target size. So we have the combination process with the circles that we can use it to get our target size. That was the positive part of the flotation, but we used different slags, and then there was something that went wrong. Like we had a flotation for some slags that didn't work at all, or we tried to use a master K for the breakage, but it didn't work. So the question was that what happened? What was wrong? Let's look at it differently. So we used mineral liberation analysis to look at the slag again and see what happens on the surface of the particle. Are we just reducing our particle size, or something happens on the surface?
Seema, just a reminder. Yeah. Just a reminder, you're over time. Please try to conclude the talk.
Okay, sorry. So to sum it up, here we use this texture analysis to develop a method that cluster all the phases together, and then based on these, we can look at different values and then put different phases together and design the process again. So we can use three different views, from the phase traits, from the textural links, and from the breakage preferences, to see how the process changes based on these points, and then use different clustering methods like K-means and graphical based similarities, and build our view. And then we can see that, okay, where are our phases? Where do we find them? Which particle size we have? How are they liberated? And based on all these views, we can develop new processes and focus on different separation methods. What we can do later is that we can put breakage models into this, or use flowsheet simulation, and then achieve better processes. So at the end, I would like to thank you for your attention, and all the people in EPAD and Federal Ministry of Research and Technology for providing the finance. Thank you.
Okay, thank you, Seema, for the great talk. A really interesting presentation. So we are running a bit behind on time. So without any further ado, I will give the stage to Bokani Moya for her talk. So please take away the stage.
Can you hear me?
Yes, loud and clear, Bokani.
Oh, okay, cool. So good morning, everyone. Good afternoon, good evening, wherever you are today. The title of my talk is Enhancing Diamond Breakage Classification Using the Morphology of Natural Stones. So this work is in collaboration with the Department of Chemical Engineering at UCT, as well as the Department of Geological Sciences. So the idea and my goal today is for each of you to learn at least one thing about the diamond processing circuit, essentially. So my work can be broken down into three phases, right? So the first being characterization, the second being experiment, and the third being simulation and model. So under the characterization phase, the research objective is to first characterize the breakage of the primary and secondary morphologies of the diamonds in the sample set. And then under experiment, the objective is to experimentally replicate the shear and impact forces applied to the diamonds in a typical combination circuit by using experimental proxies. And then lastly, we want to develop a preliminary model for small and micro diamond breakage through impact and shear stresses using DEM software. So the first hypothesis linked to the characterization of the sample is that diamond breakage is non-random and governed by crystallographic factors, leading to distinct breakage behaviors between primary and secondary morphologies. Now, the second hypothesis linked to the experiment is that the experimental replication using crashing proxies will reveal specific breakage patterns, thereby showing that breakage of the diamonds is non-random. And lastly, the distribution of forces of diamonds as simulated through the DM software will correlate strongly with those identified through laboratory and analytical methodologies. So for today, I'll focus on the characterization of the sample. Right. So essentially, sorry, just wanna minimize this. Okay, I got it. So essentially a bit of background, right? Extraction of diamonds involves the crushing of kimberlite ore. However, diamonds are mechanically broken because of impact and shear forces applied during this crushing. Now, this raises a problem, in that size reduction of diamonds reduces your critical revenue. And so we all know, like, the reason why we go into this mining precious metals is to get, like, it's for profit, right? And so now once you reduce or you break these diamonds, you lower your revenue, and that becomes a problem. So the objectives of this section of the study is to characterize diamond breakage, taking into account the diamond morphology, and secondly is to link breakage progeny to breakage mechanism. Now, on the slide is a historical diamond beneficiation plan. So a diamond circuit is very basic, right? You have your primary crushers, you have DMS, and so there's no flotation. It's a very simple processing plant, right? And we've identified 4 regions whereby we expect the diamond breakage to occur. Now, I must give note in that traditional circuits or traditional diamond circuits weren't built to minimize the breakage. Now, that's an issue. But however, newer flow sheets use HPGRs, which have seen to reduce this breakage. So the study is essentially a case study from the Roberts Vector mine, and the diamonds used in our sample are from this mine. So it was discovered in 1905. So looking at the timeline, it's likely that the same processing plant that I showed in the previous slide is essentially the same processing plant that we expected our diamonds to have gone to, right? So the mine operated for about 40 years, and it had an average grade of 0.45 carats per ton and a total production value of approximately $44 million over the life of mine. And again, so essentially a bit of background about the diamond morphology. So the shapes of these diamonds can be classified into essentially some 5 broad shape classes, right? So the A, this is your primary octahedra, right? So and then you have your makel, which is B, and then you've also got aggregates. So an aggregate is essentially where you've got 2 primary stones and they grow within each other, right? And that's how you form that shape. And then you do get your secondary stones. So these arise due to geological and chemical processes, which is essentially round the stone, creating a dodecahedron, and then tetrahexahedron, also known as THH shaped stones. And then you could also get irregular or broken stones. So this is essentially like a summary of like the statistics that we got from the parcel, where we looked at or processed rather 6,288 stones. And I think the only thing of note is that you had your octahedra being the highest frequency within the parcel. And then we also employed various imaging techniques for the analysis. So the first being optical microscopy, which allowed us to essentially be able to identify morphologies within the sample. It also allowed us to identify the presence of any mineral inclusions and also to be able to tell what color our stones were. And we also did some scanning electron microscopy, which allowed us to also identify the surface features, identify cleavage planes, and differentiate between the different inclusions. As what we saw was you could not tell whether a dark spot on the diamond would have been a sulfide or a graphite inclusion. So an inclusion in this case is essentially it's a mineral that grows within the diamond and usually has an area of weakness within this diamond. And so the third imaging technique that we used is X-ray computed tomography, which allowed us to observe how fractures propagate within the diamond. We could essentially determine the depth of the fractures, the crack propagation patterns, and quantify these things. So these are the methodologies that we use in our analysis. And so I mentioned before that diamond breakage has something that's long been studied for a long time, right? So there exists only one diamond breakage classification system, which was developed by De Beers in 1978. And so with this one, they only looked at material loss as a measure of diamond breakage. However, the work that we're doing is an extension of the De Beers classification system, in that we look at material loss as well as the influence of morphology, and also look at whether if the breakage is non-random or is it influenced by morphology, which were essentially the limitations of the De Beers classification system. Okay, so I heard someone. So essentially we could essentially group this this classification algorithm into 4 parts. So the first being the surface features, and then you have irregular breakage, crystallographic breakage, as well as a decision block, right? Which I'll obviously go through in the next slides. So surface features would essentially be classed in the 1 to 5% breakage loss region. Would group these as abrasion and attrition. And so essentially they were classified between, so the ones we identified were pitting structures, irregular abrasion pits, trembling abrasion pits, and abrasion pits on that crystal edge. So on the slide, you can see the examples of the stones that we saw in our sample. And then with irregular breakage, you had essentially either random or coincidal. So random being the breakage was not on a crystallographic plane, and coincidal was like sort of like a curve type of breakage, which we also noticed in the sample. And thirdly, there was crystallographic breakage, right? So this breakage was along crystallographic planes. You could see, so you get these sharp fracture patterns that we noticed that also were in our sample. And then the breakage decision block, where we essentially grouped our stones based on the amount of material loss that the stones had. Right, so assessing fracture behavior. So there's 4 key things that I want you to take away from this graph, right? So the first is when looking at the irregular breakage when an inclusion was present, you notice that there's a higher proportion of secondary stones within this group, right? And then compared to an irregular breakage where an inclusion was present, right? Where you notice that it's somewhat of a similar number between the primary and the secondary stones, right? And this can be explained by your secondary stones being more rounded. And so you notice that the stress distributes more evenly. So you're more likely to see that any breakage that will occur within the secondary stones will essentially have to be irregular, right? And not of a crystallographic plane. And when inclusion was present, you had an equal amount of a breakage between your secondary and your primary stones. And then this is also evident from the crystallographic breakage within when an inclusion was present or when inclusion was absent, in that you had a higher proportion of primary stones within this puzzle, right? Signifying that you had your primary stones were more prone to crystallographic breakage due to their shape, which was essentially because once you have, like, for example, like a very sharp edge, right? That's where you expect that breakage to occur. And this is what we saw in our puzzle. And then I did mention, so what inclusions were, which these are essentially regions of weakness within the puzzle, right? And so we noticed that you had heavily broken stones were 2.4 times more frequent when inclusions were present, compared to 38% in stones without inclusions. Thus, the presence of inclusions promoted more severe fragmentation. So essentially, conclusions from phase 1, right? That the De Beers breakage classification system, it distinguished breakage severity by percentage loss, but it lacked correlation with specific comminution mechanism. And that we established that breakage is not random, right? It's strongly influenced by the stone morphology. And the primary morphologies mainly show crystallographic breakage, and inclusions drive random fracture propagation in these diamonds, causing irregular breakage. So the existing classification system is rather descriptive rather than diagnostic, meaning that it characterizes the breakage severity but does not reveal why and the how. So essentially, it does not reveal the underlying mechanisms of our breakage. So it's important to determine the mode of breakage to essentially enable better process modeling and mitigation strategies. So now let me take you through the initialization of phase 2 and 3, right? Which is essentially modeling the diamond breakage through the aim of it is to model the diamond breakage, right? And in this case, we want to replicate the shear and impact forces like I've mentioned already. And the key metrics in this case would be to determine the force energy level required to initiate the breakage and to be able to reproduce the breakage patterns we noticed in the parcel. And then in this phase is when we'll employ our short impact load cell tests, right? On different morphologies. And our phase 2 is to develop a preliminary model for small breakage, diamond breakage through impact and shear stresses using the DM software. And what we want to get from this is impact force distribution through the diamonds and the accuracy of the simulated fracture planes, right? And this is where we perform our DM simulations. So this on the slide is essentially a schematic of a short impact load cell, right? It's a very simple construction. And then from there, all it does is it's just you drop weight and then you break your diamond, and then you can get essentially 3 parameters. So we can get the force required to initially fracture the diamond, the strength of the diamond, as well as the total energy absorbed by the particle for breakage. And then, so phase 3, this is where we do our DM simulations. And so we have a range of parameters that we're going to investigate by keeping a few parameters also constant, which is the stool ball size and the particle size. We'll then employ varying drop heights, different orientations. So where we have it's or flat on its 111 plane, or when the apex is up, as well as look at the 2 shapes. So you have an octahedral shape and a dodecahedron shape. So this is the plan going forward. And before I finish, I'd like to thank Center for Minerals Research, Excite, National Research Foundation, CIMERA, and the EBE at UCT and also lastly, John Gurney for essentially donating the diamonds for this study. Thank you.
Great talk, Bukani. Lots of diamonds in there, and you're breaking them. Expensive stuff. But good. So the up next in the line is Vivian. So Vivian, over to you, please. Take it away.
Shujat, I think we have a short question and answer session.
Oh. Sorry. Yeah.
Before,
okay,
thanks
for reminding me, Meg. Sorry. Okay, so let's proceed to then question answer session. So I think floor is open for the questions. Anybody who wants to post, feel free to unmute, or if you want to just add your questions to the messages.
So I can answer the question from Rodrigo. So the DM software we're going to use is we might use Rocky. So we're in the process of looking at whether we want to use Rocky or just the EDM one. And the breakage model, it's going to be a bonded model. That's what we're going to use. And then the question from, I don't know if is going to answer that question.
So you answered the first one, right? And now the next one is from Marcelo Tavares. And the question is, why are you planning to use different drop heights if impact load cell would be used primarily to identify primary breakage?
Thank you, Marcelo, for the question. We want to use different drop heights. I guess it's more of how do you say, there's a certain word I'm looking for, I'm just forgetting it. But we want to, give me a second, like there's this word that I'm looking for. It's like by using the different drop heights, you are, the word I'm looking for is really, wait, it's really, wait, give me a second. Like, I'm forgetting the word.
Maybe I can answer the questions and then Bokani had time to think.
Yeah.
So to answer Professor Lieberwort, we use a rotor impact mill with the constant speed and we didn't sieve. And to Rodrigo, the scale of operation, it depends on how much of the engineered artificial minerals are available. The problem is that it needs a lot of time to cool down because it should be controlled. So I think to scale up would be like at the beginning, at least 50 kilo per hour to start with, but maybe later when everything is running, maybe more. I hope I answered the questions.
Thanks, Seema. And then we go to a question for Bokani again. I'm not sure if there is a ball mill in diamond comminution or perhaps a scrubber from your flow sheet.
Hi, Leseka. Oh, so Marcelo, the word I was looking for was validate. So we just wanted to validate the DM model and the silk. That's the word I was looking for. It's just to validate it. And then for Leseka, I'm not sure if there's a ball mill. Oh, so there is a scrubber. I'm not sure if you saw it, but on the flow sheet there is a scrubber.
Okay, thanks, Bokani, for answering questions. We will leave the floor open for questions for a few more minutes. Somebody has, please feel free to add your questions. Okay, seems like nobody else has any other further question from the first two presentations, so we can use that time and we can move to the 3-minute snapshot presentations then. So I would like to invite Vivian to come around and please take the stage and present your work on microstructural control on the fragmentation of iron ores, please.
Thank you. Good morning, everyone. My name is Vivian. So I will talk today about the microstructural control on the fragmentation of iron ores. Well, the primary breakage characteristics of ores can be described by their primary energy fracture, their amenability to accumulate damage, the size distribution of the fragments after breakage, and the distribution of different minerals in the size classes. And all of these are responses of the breakage characteristic of the ore, which are also a response of machine-specific properties, but what we are interested here are material-specific properties such as mineralogy and microstructure. And if we are able to relate how these ore characteristics relate to the breakage and liberation responses of different ores, we are able to better predict the comminution and liberation responses of ores, and then tailor the circuits to promote preferential liberation when non-random breakage is relevant in the breakage of the ore. Well, the objective of my study is to assess which mineralogical and microstructural features actually influence the breakage of iron ores. And I will do this by comparing their breakage behavior, which I obtained through single particle tests, breakage tests, with their mineralogical and textural characterization, which was done with these techniques here. Well, looking at two extreme cases, which I will show here, are the jasper-like samples, which have very high packing density, tight grain boundaries, and cementing by secondary goethite, which causes this sample to show very high resistance to primary breakage, and explains also their low breakage intensity and low amenability to accumulate damage. When we look at the other extreme, we have compact taborite sample, which is very typical from Brazil, And its oriented grains of hematite, weak grain boundaries, and high porosity explain its low resistance to primary breakage, its high breakage intensity, meaning that it fragments into fine particles after breakage, and its high amenability to accumulate damage. When we look at the way fragments are distributed in the different size classes, we can see the difference in the size curves for all the studied samples. And the two extremes here are the jasperite sample, in which we see a very uniform distribution of fragments among all size classes, and the compact taborite, in which we see almost a bimodal distribution of fragments. When we look at the mineral deportment in the different size classes, we can see a higher difference between hematite and quartz for the compact taborite, indicating its preference for preferential breakage. And the jasperite sample shows a very uniform distribution of quartz and hematite among all size classes, indicating its natural susceptibility to random breakage. Well, the next stages of this study involve the quantification of ore properties, the assessment of intrinsic liberation responses through MLA analysis before and after controlled breakage of single particles. We are also going to be able to assess the proportion of intergranular and transgranular fracturing and associate all of these breakage characteristics with the mineralogy and texture of iron ores in a more mathematical way, with the final objective of predicting breakage behavior and liberation responses through ore properties. Thank you, everyone, for the attention.
Thank you, Vivian. Very good talk. Okay, so now the next one in the list is our very own Max. So Max, over to you.
Okay, thank you. I think you can see my screen now. Yeah, short introduction again. I think I forgot that. My name is Max. I'm currently working in Braunschweig at the Institute for Particle Technology, where I'm doing research on multi-component comminution, especially in steric minimals. And yeah, today I really want to focus on the investigation of the so-called protection effect. So when we are looking at comminution processes on an industrial scale, we can usually find an extremely diverse range of products, which can be the production of construction materials, the processing of ores, and also applications in recycling. And especially for ores, it's more or less impossible to predict how and where a particle is going to break when we are looking at the extremely heterogeneous structure of these particles. And also we have to keep in mind that for multi-component comminution, we don't want to achieve narrow particle size distributions, but we want to achieve a selective comminution, which helps us in the separation of valuable and non-valuable materials. In the past, I conducted already some tests and or various tests on the influence of the material hardness, for example, and also the influence of the feed particle size. And one effect which has been discovered or seen quite often is the so-called protection effect or shielding mechanism. Thereby, large particles are protecting finer particles from being stressed by the grinding medium. And right now I have the idea to incorporate this effect into my population balance model. And therefore, I want to have a quantification or to get at least a correlation of process parameters and the protection effect. Therefore, I want to use a drop weight test, which consists out of a magnet, a steel ball, and the steel ball is usually falling on a particle layer. It's a monolayer, which is arranged on a pressure measurement foil. And the arrangement of particles is usually done in a hexagonal way. And we can either test same-sized particles, but also particles with one protecting particle located within the center. With my test, I do some evaluation. The first one is the pressure measurement foil, which is underneath the monolayer, which gives us an idea about the pressure pattern. And also we're getting some video images and see how particles are being stressed. some first results. On the left-hand side, you can see a monolayer of limestone particles, and in the middle, you can see some limestone particles surrounding a coarser quartz particle, and underneath you can see the pressure patterns and also the proportion of colored particles, which it gives you an idea about the pressure which is set or put onto the monolayer of particles. And indeed, in this case, we can see that this coarser particle within the center is reducing at least the area of intensively stressed particles. Within the future, there are some more investigations planned. This is only the first trials, and we want to do a variation of the particle size ratio, variation of the ball size, and also, of course, for the variation of the stress energy to find out some correlations which can be implemented into population balance models. Thank you.
Thank you, Max. Great talk. Really enjoyed it. And now we go to the next one, and the list is Amriti Mohit from University of Queensland, JKMRC. And she got a talk around ag milling behavior, understanding ag milling behavior under variable feed conditions. So over to you, Amriti.
Hi, is my audio working?
Yes.
Oh, perfect.
Loud and clear.
All right. Hi, everyone. My name's Amriti. I'm a first-year student at JKMRC, and I'll be presenting my research topic on autogenous grinding mills. So over the recent years, ag mills have gotten a lot more industry focus, particularly because they don't use steel grinding media, meaning that they have lower operating costs as well as a lower carbon footprint. The challenge is that they're highly sensitive to changes in feed competence as well as size, and the resulting effect of this is not largely understood. This makes them quite difficult to operate stably in practice and also difficult to predict using existing steady-state models. So this has really sparked a lot of interest into, can we actually build a fully dynamic and mechanistic ag model which incorporates the effects of blend characteristics and how we actually operate the mill? So there have been many efforts put into modeling the individual sub-processes that happen in tumbling mills. However, we're still not at a condition where we can actually predict how mill content evolves with different blends and what the corresponding breakage response is. So what we often see is if there's lots of competent in the feed, the mill will build up. Alternatively, if there's lots of soft, the mill will underload. These are examples of currently unpredictable mill behavior, which leads to instability. So the aim of this research is to understand what causes these effects and understand it, and hopefully integrate the findings into a fully dynamic and mechanistic model, which really builds on the existing work done in this space. So to do this, we need to build a robust data set which really maps out mill performance over a range of different blends, which will be characterizing using both novel ore characterization methods as well as the classical methods. And from there, for each feed condition, construct grind curves using lock cycle pilot tests using a pilot mill. And the critical part of the experiment is actually measuring and characterizing the mill content. So with that, we'll have like a very rich data set showing how feed content, mill content, and product change with different operating conditions, which will really give us insights into how the breakage environment affects mill performance and where we're getting optimal and suboptimal performance. So from there, we'll integrate the findings and really build the framework for a mechanistic model to validate at full scale. So there's lots of value in this project, especially now that we do have faster and more accurate ore characterization methods. So developing the understanding as well as the tools to make more informed decisions in regards to what gets mined, what gets blended, and also how to operate the mill can really help mining companies with attain both production and energy reduction targets. With that, I'll conclude my 3 minutes.
Perfect. Perfectly great on 3 minutes. Actually, a little below 3 minutes. Great talk. Really enjoyed it. So with that, the last presenter for today and for this competition is Please forgive me if I pronounce your name not right. Thales Gamma from UFRG.
Thales.
Oh, Thales, yeah. I'm sorry
Yeah,
for
can
that.
you hear me? Yeah, Thales.
Yeah, Thales.
Okay, so
yeah, take it away, Thales.
let me share my screen for just a moment. So I believe, do you already see my screen or not? My presentation?
Yes, we do. We do. Yeah.
Let me put that aside so I can start. So good morning, all. Today I will present our work on the UFRJ mechanistic model and its application on autogenous grinding or SAG mill. It's a small portion of my PhD work, and my advisors are Professor Marcelo and Professor Rodrigo. Okay. So SAG milling is a cornerstone of mineral processing, but it's a complex challenge. It's highly energy intensive, and the traditional models we use for optimization and modeling have significant limitations. They tend to be site-specific, lack universal applicability, and crucially, they don't explain the underlying physics inside the mill. This makes it difficult to predict how changes in ore characteristics, ball charge, or operational parameters will truly affect performance, mill performance. So this is the problem we are addressing with the UFRJ mechanistic model. This isn't a curve fitting exercise. It's a physics-based model designed to understand and quantify the root cause of mill behavior. It was first developed for ball mills by Professor Carvalho and Professor Tavares, and now has been successfully adapted for SAG mill for over a decade. So its key objective is to simulate the internal mechanics of the mill by coupling two powerful techniques: the discrete element method, or DM, which tracks the motion collisions of the charge, and the population balance model, or PBM, which simulates particle breakage, including both superficial and volumetric fracture. So here how it works in practice. It starts from a non-initial charge. The DM simulation generates collision energy spectra. So this data feeds the mechanistic model, which calculates particle breakage and transformation, and damage accumulation over very short time steps. Crucially, when the charge changes significantly, a new collision energy spectrum is generated, and then the cycle restarts. This iterative process allows us to track the evolution of the new internal charge accurately over time. So just to show you some of the model capabilities, here this chart shows a simulation of a copper ore pilot mill grind out test. It predicts the discharge rates, as you can see here, of fines, and the hold up of the coarse rocks through the entire simulation time span. You can see here the top size, and the top size lingers inside the mill for a moment, and then it's rapidly breakage. So the next critical step in your ongoing work is to validate these curves against experimental data from a physical mill. This validation is essential to confirm the model's accuracy and its ability to truly capture the complex physics of SAG milling. So thank you very much. And that's my contacts for further questions.
Brilliant. Okay, so that was the conclusive talk for the day, or night, or evening, or morning, wherever you are. So we are a bit behind the time, and let's jump straight into questions. I see a big pile of questions in the chat already, and we need to respect some time as well. So let's get going. We'll see how far we can go with that, and then we may need to skip some questions, however. So first questions for is Vivian from Rodrigo. Can you comment more on the relationship of breakage model parameters and iron ore type?
Yes, thank you for the question. I didn't have time to present all of the results today, but yeah, we found some interesting relationships between, for example, D0, which is a parameter from the model that describes the variation of medium-specific fracture energy with particle size. So D0 represents the characteristic size of the material's microstructure, and we found that for these very typical taborites, which are controlled by the reactivation of these intergranular fractures, we found lower values for D0, and for samples which we believe that are mostly broken by the reactivation of larger fracture networks that act more as a brittle materials, we found higher D0 values. So I think this is the most relevant relationship that we found from breakage model parameters. I hope it answers the question.
Thank you, Vivian.
Thank you.
Now, the next question I see, Max got lots of loaded questions. So the first one is from Marcelo Tavares. Did you compare your results with predictions from our model, Barrios et al. 2011?
Yeah, I can try to be short and answer like most of the questions. So yeah, I did not compare it until now because right now I'm just checking out which pressure measurement system is actually working, and yeah, there's lots of refinement to do, like about a proper yeah, experimental setup. So this will take some time, but of course sooner or later it's the idea to yeah, go the same direction as I forgot his first name, but the same way as you did in the past. Commenting on Grant's question, of course, there's also sometimes, especially in dry grinding and the stressing of particle beds, we usually also see that fine particles are surrounding bigger particles and thereby yeah, protecting the coarser particles. This can happen, but yeah, especially when we are looking at HPGR, for example, this happens, but also sometimes in dry grinding for ball mills. Next one is Rodrigo. In this case, the limestone particles were softer or weaker. And last but not least, maybe the question of Professor Lieberwirt. Yeah, we did some investigations similar to Fürstenau and Kapur about the joint comminution of limestone and quartz, and also there could be seen, or we could evaluate this kind of energy separation factor or efficiency factor, I would call it. So which component is yeah, taking up which specific energy, and so the results somehow align with each other, but what we can see is especially that there's a particle size dependency, and this couldn't been figured out in the past, and but there's yeah, of course, this particle size dependency, and this is also why we are doing like this kind of protection effect investigations right now.
Right.
Thank you.
Yeah. Have you addressed also the particle shape effect? So we had also a question regarding that. Max?
I see it now. Yeah, I haven't done it so far, but yeah, this is probably going to also influence my results, especially like for the quartz particles. It's not such a big problem, I would say, but especially the limestone particles, yeah, they sometimes are irregular shaped, and so maybe I have to check another supplier as well and compare particles, but I guess in the end there will always be a shape influence. Yeah.
Brilliant. Okay. Any questions that remain unanswered, please feel free to reach out to the presenters later. I'm sure like they, especially Max loves answering questions, as I could tell. Reach out to him directly. So the last question is for Amriti and from Rodrigo. Among all the challenges regarding egg milling, sag milling models, which one do you think is the most critical at the moment?
I would say the breakage and transport. So at the moment, some models put them together, lump them together. But what's good with our test program is that we're really decoupling the two so that we can gain a better understanding of the breakage response. And then from there, in regards to pulling the model together, we'll just be looking at what is available in terms of transport modeling and trialing the different frameworks to see what works best.
Thank you, Amriti. I'm just eyeballing if we got any hand raised up in the chat or in the audience. Well, if not, so I will conclude the session and we will now get to the judging part. And we need to do a bit of contemplation there. And we will circle back around at around 9:45. Please stay with us. Stay in the call. We need to jump out of the call and then we will come back, join you guys again.
Yes, and for the judges, we set out an appointment, so another meeting where we can meet.
Sure.
Yeah. See you in a bit.
Yeah.
Right, back in.
Yeah, we got 2 minutes to go, so the reconvene was 9:45.
Oh, everyone's gone off for the coffee break or whatever.
I think it's the time to now announce the winners.
Time to celebrate. Okay, shall I kick it off?
Let me have a look at that. I think, yeah, we got a fair few people in the audience at the moment. Maybe just give another minute or something like that. And
You can't tell who's active and who's just get out the room.
yeah, okay. Yeah, please, Sherry.
All right. So firstly, we were very pleased with today's presentations. You guys all showed a great depth in the research that's happening within the institutions that associated with the GCC, and this is never an easy job to do, but we are very grateful that we have the opportunity to do this. So I'm not going to waffle too long. I'm going to start off with the 3-minute presentations. I've got 3 honorable mentions, and then we'll give the top prize. So we've got honorable mentions to Philip, Nebel, Amriti, Mohit, and Max Tubabin. You guys all did really, really well. But we have a winner that everyone agreed on, and that is Vivian Martino. Well done. We all felt that you were very clear on your objectives for your presentation, and you managed to get a great deal of depth presented in that 3 minutes, which allowed the clarity of your presentation to be very, very good. So well done on that one.
Thank you very much. Thank you.
All right, and then the 15-minute presentations. You guys should all be very happy with what you've done. You are almost at the end of your research journeys and hopefully not leaving the GCC anytime soon. So I've got an honorable mention to Bukani. We felt like he did a really good job. And then our first prize is going to go to Rodrigo Prates. Congratulations. Your presentation was very clear. You had well laid out objectives, and your slides were very, very informative. And you showed a very solid research process to, well, that you, sorry, let me try that again. Solid approach to your research. So congratulations. I don't know, Holger, welcome. Do either of you want to say anything to close?
Yeah, so I would say thank you very much to everybody who was presenting. I think we had great presentations, very interesting topics today, and I think the next generation is in a good path for bringing forward the comminution topics, and we see particular. I was impressed by Vivienne for this combining the material topics with the comminution itself. So there is it's a challenge, still a challenge for many, and so I think it was very good. Congratulations, and of course also congratulations to Rodrigo, to the winners, and but also to everybody else. I think it is important that we have the chance to compare each other, to see what the others are doing. I mean, you are the next generation to talk to each other and to collaborate worldwide. Thank you very much to you. Thank you very much also to the organizers here, in particular to Julia and Sherry and to Max, Shujat, all the management team who did a great job in organizing this competition again. So I think we had a very splendid and very smooth presentations today and the conference. So thank you very much to all of you, and of course also to the people who had the difficulty to judge here, to Malcolm, to Marcelo, Rodrigo again. So I think it was a good working day, and so I think we are looking forward to seeing each other, maybe hopefully next year, when for the next Students' Day, GCC Students' Day. Thank you very much, and have a good time, everybody. Good Christmas period for those who are celebrating Christmas, and for the others, have a good time, simply.
Thank you. Thank you,
Before
Holger.
everyone drops off the call, Grant had a great idea that we could have everyone turn the cameras on so we can take a screenshot for our social media.
That would be a good idea. Yeah, everybody. Should I snow the snow avalanches here in front of my windows here? every now and again, see some snow.
Well, there'll be some in the day, some at night. It'll be great.
Yeah.
So who's taking the screenshot?
It's currently a really boring screen that I've got.
Everyone has to turn their videos.
I just see 9, which is now.
Can you actually capture all of the participants or only?
I don't know how to.
Okay.
Yes, I'm struggling with that as well.
You do one.
You only get 4x4,
I can.
16 people.
No, I've got it on all 49. I've got, if you go to at the top, you can go view, and then under the settings you've got select max gallery size, and then you can select 49, and then you can get everyone.
Oh wow.
Grant, a takeaway for all of us today.
Yeah, I think you do it. Yeah.
Yeah.
All right.
Brilliant.
Everyone ready?
Relaxing. Many people.
Okay. Oh, that's recording. I want to take a camera. All right. Smile and let's go for it. Oh.
Did we
All
get
right,
it?
that looks lovely. We got it. Yes.
Okay, perfect. So
Thanks.
wish you all the time over there, and thanks everybody.
Yeah, thank
Thanks,
you.
everyone.
Well done.
Thank
you, guys.
Thank you, everybody.
Thank you.
Team.
Bye-bye.
See you later.